Giorgia is currently at the King's College in London, and a lot of very innovative work is coming from there. And last author is René Bottner, who is also working with a whole team of people on novel methods, especially techniques that would allow for relatively fast acquisition of CMR data without a lot of interfering with the scanner. And so thank you very much, Giorgia, for joining. And for 10 minutes, the floor is yours, and have us walk through your paper. And please have everybody unmute yourself if you don't speak. And if you have questions, just put them into the chat box, and then I can ask them for you. Okay, Giorgia, stage is yours.
Can you hear me all right and see the screen?
Can you try again? We can hardly hear you.
Can you hear me now?
Can you get a bit closer to the microphone?
Okay. I think this is better.
Not really.
Is it better now?
Yeah, that's much better. Okay.
And you see the screen as well, right? Okay.
That's not as good as before. It was better for a while.
Like this is good.
You're trying to use a different microphone. Okay, maybe just get started. We'll see.
I can't hear. Can you hear me?
Yeah, if you speak up a bit, and maybe you can increase the input in the Zoom settings and the Zoom preferences, but maybe in the interest of time, you have to just go ahead.
Okay.
Yeah, that's good, actually.
Okay, that's good. Okay, so I'm Giorgia, Milotta. Thank you for inviting me at Discord Journal Club. And in our work, we propose a motion-corrected 3D whole heart imaging sequence for the simultaneous acquisition of bright blood images, black blood images, and also co-register T2 maps in a single scan of about 11 minutes. So conventionally, anatomical images and quantitative images such as T2 maps are acquired in different way with different sequence. In particular, 3D bright blood and black blood images are usually acquired in free breathing with 1D diaphragmatic navigators in order to get the acquisition. However, this approach have a low scan efficiency and can lead to prolonged and predictable scan time. On the other hand, 2D T2 maps are usually acquired in short axis orientation in several breathholds, and usually 3 slices are acquired at the mid, base, and apex of the myocardium in order to obtain the total coverage. However, this technique have a low spatial resolution and so also limited coverage. Furthermore, in order to obtain a comprehensive assessment of the whole heart anatomy and quantification of the myocardium, several sequence needs to be acquired in different orientation and different breathing condition. And this could lead to long and unpredictable scan time and also possible misregistrations between the different images. So that's why in this work, we are proposing one single sequence in order to obtain co-register 3D bright blood images, black blood images, and also T2 maps. This novel sequence requires 3 key ingredients. The first one is a variable density trajectory in order to accelerate the acquisition. The second one are image navigators in order to gate and correct for the respiratory motion, enabling 100% scan efficiency. And the third one is a matching step used in order to obtain the T2 maps that is similar to what is performed for fingerprinting. And this allows us to avoid the recovering heartbeats for magnetization recovery. So the framework of the sequence is here shown in figure 1. We acquire 3 interleaved data sets. We have a variable density spiral-like Cartesian trajectory with acceleration factor of 4, and we are also acquiring these image navigators prior each volume in order to correct for superior, inferior, and left-right respiratory motion. each of these set is acquired with different preparations. In the first one, we have a T2 prep inversion recovery model. In the second one, a T2 preparation, and the third volume is acquired without any preparations. Each of these volume is then reconstructed with a 3D patch-based reconstruction called qBOOST. And the first one is used as bright blood images for anatomical visualization. The black blood volume is obtained by performing a phase-sensitive inversion recovery reconstruction between the third set and the first set. And the T2 maps are generated by matching the acquired signal evolution to a simulated dictionary obtained via extended-phase graph simulation. As I said before, this is really similar to fingerprint matching. However, we are only matching 3 points that correspond to the 3 different contrasts that we acquired. This sequence has been tested first in simulation and phantom experiments in order to evaluate the T1 and heart rate variability, and also the T2 accuracy with respect to a spin-econ experiment. The results of the simulation experiments are here shown in figure 2. And we are plotting on the y-axis the matched T2 as function of different simulated T1s and different simulated heart rates. We can see that from T1 ranging between 800 millisecond to 1400 millisecond, we obtain a T2 variation of less than 5%, whereas no variation was observed for different heart rates. From the phantom experiments, we evaluate the accuracy of this technique with respect to a spin-econ experiment, and we obtain a really high linear correlation between this approach and their phantom reference values. Although we have overestimation of long T2s, and this could be due to a not sufficient encoding of long T2 values, since with the longest T2 preparations that we are using in the sequence is only 50 milliseconds. However, the same behavior was also observed with a standard 2D BSSFP T2 prepare mapping sequence that is here plotted in gray. We also acquired 11 healthy subjects and 4 patients, and moving on to the healthy subject results. In figure 4, we have these 2 representative healthy subjects reformatted in different orientation. Indeed, we are acquiring the volumes with a resolution of 1 by 1 by 2, and thus the nearly isotropic nature of this acquisition allows us to reformat the volumes in each orientation we prefer. In this case, we have short axis, transversal, and 4 chamber. And we can obtain the bright blood volumes, the registered black blood volumes, and also the T2 maps. From the bright blood volume, we can appreciate a good delineation of the anatomical structure and papillary muscles, whereas from the T2 maps, we have a uniform T2 quantification through the whole left ventricle. We actually quantified the uniformity of T2 quantification for another healthy subject that is here shown in figure 5. We have a total coverage from the apex to the base of the myocardium, and again, the bright blood, black blood images, and the co-registered T2 maps. And we obtain a really uniform T2 quantification as shown from the whole left ventricle histogram and also from the T2 distribution through different slices. Similar results are also observed in the 17-segment model. And in the 17-segment model, we also evaluated the standard deviation within each region of interest. And we can observe a higher spatial variability in the inferior part of the heart that could be due to residual motion artifacts or inhomogeneities at the edge of the field of view. We also compare this technique to standard techniques, and particularly for the bright blood acquisition, we compare it to a fully sampled CMR that was acquired as well with image navigators, so that the acquisition time of the proposed technique, qBOOST T2 technique, and the CMR was similar and about 11 minutes. But with the proposed approach, we also obtained the black blood volume that's here shown, and also the 3D T2 map. In terms of image quality, we obtain a really good delineation of anatomical structures, such as the coronary arteries, and we also obtain a really nice contrast between the blood and the myocardium, similar to what is obtained with a standard T2 prepare CMR. For T2 quantification, we compare this sequence to a standard T2 prepared 2D T2 map. And the 3D volume that we acquired were reformatting to the same slice location that was acquired in 2D. And this is shown here for 10 healthy subjects. And again, we have really good comparable image quality with the standard technique. So we have the standard techniques and the proposed sequence. We also obtain good results in terms of T2 quantification. They are shown in figure 8. In particular, we observed a slightly bias of 2.71 milliseconds and higher spatial variability. However, in the left ventricle of the segment. And this analysis was also performed on the 17 segment models, and we are showing here results in this case, in which we calculated the variability of the standard deviation measurement in each segment with the proposed technique to the standard deviation measured with the conventional T2 map. And again, we have a higher spatial variability. However, this could be not influenced by the different image modalities, but also by different imaging parameters. Indeed, we investigated this in supplementary figure number 2, that I can show you here, in which we investigated the effects of averaging continuous slices, and so decreasing the resolution of the acquisition on the spatial variability. In this case, we can see that by averaging 2 or 3 slices, we really decrease the standard deviation in a region of interest, and we obtain similar value of what was observed in a standard 2D acquisition. We finally acquired 4 different patients, and these patients were patients with suspected cardiovascular disease and were indicated for cardiac MRI scan. However, in our case, we didn't identify any pathologies related with T2 elevation, either with our approach and with clinical scans. But however, again, we obtain a really nice image quality comparable to the acquisition, and with our sequence, we also have the bright blood and black blood volumes. So in conclusion, we proposed a free breathing 3D sequence for the simultaneous acquisition of bright blood images, black blood images, and co-registered T2 maps in a scan time of 11 minutes. And we proved the feasibility of this sequence in 11 healthy subjects and 4 patients. However, future work will require the acquisition of a larger cohort of subjects, of patients, in order to evaluate the capability of these techniques to identify elevated T2 associated to other pathologies. And with this, I'd like to thank you for your attention. And if you have any question, I would be happy to answer.
Thank you very much, Giorgia, for walking us with a pretty high speed through this very technical paper. And congratulations to the results. So in short, what you can say is that with this sequence, which arguably or admittedly still takes about 11 minutes, but you get basically a 3D data set that gives you T2 information as well as an angiography information. So could be useful in patients with, for example, a suspected acute coronary syndrome, where you could look at both the anatomy, including coronaries and edema. So the scan time, people may say, okay, 11 minutes, that's still significant scan time. Any ideas whether this could be shortened in the future? So working with even more sparse data sets, or do you think that is it in terms of the scan time?
We are actually investigating it. So we are trying to accelerate the acquisition even further, reaching like an undersampling factor of 6 or 7 in order to obtain an acquisition time of about 4 minutes, and use another kind of reconstruction with neural network that was also shorter the reconstruction time. And so it could be possible to shorten the acquisition and as well the reconstruction time. But we are still investigating and acquiring testing on volunteers.
Yeah. Thank you. So whoever has a question, just either speak up, so unmute yourself and speak up, or type the question into the chat box. I have one before we hand over to Richard. You reported a bias or a mismatch between the conventional T2 and the boost results. So previous experience with fingerprinting, we had comparing conventional T1 mapping with the fingerprinting derived T1 maps, showed that the inaccuracy may actually be on the conventional side and not so much on the fingerprinting side. So do you know which results you trust more, or is it a bias or problem of the boost technique or of the conventional T2 quantification?
I mean, we are actually not sure if which one is the most accurate technique. Indeed, like in the phantom acquisition, the boost seems to be more reliable than the conventional T2 with respect to an spin echo. However, in vivo, we are not considering other effects such as an MT or field inhomogeneity. So it's actually really hard to say which one is the T2 value that is closest to reality.
Yeah. Okay, thank you. That was very interesting. So if you could unshare your screen, and then I would ask Richard Thompson from Edmonton to come up with their paper. Very cool clinical application of water-sensitive cardiovascular MR. And what the Edmonton group here came up with is looking at pulmonary edema in patients with heart failure. And I think there's a great paper. So Richard, walk us through it, and thanks for joining.
Thanks for having me, Matthias. Can you hear me?
If you could speak up either a little bit or increase your input volume, it's good, but it's not, but it could be a bit louder.
Is that better?
Yeah, that's great. Thank you.
Okay, great. So thank you very much for the invitation. I want to acknowledge my primary clinical collaborator, Ian Patterson, the senior author on this paper. So we've worked together for many years, and it was his original motivation to get us into measuring lung water. It's such a fundamental feature of heart failure. So in over 50% of patients with either acute, decompensated, or chronic heart failure, there's some kind of edema that's present. And CMR seems like an attractive tool because we're imaging water. We're used to the lungs being black in MR images, but there is a lot of water there. So our goals when the study was first to determine the relationship between CMR-derived lung water content and invasively measured left side filling pressures, because the source of the water in cardiogenic pulmonary edema are those increased filling pressures. So we want to see that relationship. And secondly, in a large clinical cohort, we wanted to see if measuring lung water is prognostic. So we had two cohorts, a validation cohort and a prospective cohort. The validation cohort were heart failure patients that were, they were sent for catheterization, so we had access to their pressures. And we also measure BNP in everyone, and this is critical because BNP is a widely available blood test that is also strongly related to those filling pressures. So we want to do better than BNP. The prospective cohort was a group of healthy controls, patients at risk for heart failure, and patients with heart failure from the Alberta Heart Study. And we subgroup those into, as is commonly done, the preserved and reduced ejection fraction patients. So all of this was done on an ultra scanner, a 1.5T Siemens Sonata scanner. And to measure water, we wanted to use something that was just out of the box and widely available. And so the single shot fast spin echo, or haste pulse sequence as it's called, actually it overcomes the short T2 star limitations of imaging water in the lungs. So it gives you a lot of signal actually. Cardiac gated, a really short echo time of around 12 milliseconds. So it's largely spin density weighted, which is what we want. And there's two different protocols we tested. One was full lung coverage, 10 to 12 sagittal slices. And there's an abbreviated protocol where we just look at one slice through the right lung, one sagittal slice. And they're acquired in such a way that we just get spin density weighting in all cases. So no T1 weighting and no minimal T2 weighting. So moving to this figure now, we just did free breathing real-time acquisitions at end diastole. And we just retrospectively selected respiratory phases that are at end expiration because we don't want there to be any signal variations due to the inflation of the lungs. We always use the liver as the reference signal. So all of our lung water values are relative to the liver, which is a pretty constant amount, around 70% water density was the assumption. We did an analysis where we looked at the whole lung volume, all of our slices in the validation cohort, just the left, just the right, and actually also an abbreviated analysis, which is just a profile in the right lung. So we're just looking at the lung signal versus the liver signal in one single profile. So some results from our validation cohort. So what we're looking at here now is the relationship between filling pressures on the x-axis, and MRI-derived lung water content on the y-axis for the left lung analysis, right lung, whole lung, and just the single profile in the right lung analysis. And this was great. As you'd want to see, there was those patients who had increased filling pressures had increased lung water content, with actually the strongest linear agreement for the profile method. And also, as expected, BMP, this blood marker, is also strongly related to the filling pressures. So onto the prospective cohort. So we have around 250 subjects in this. So there's, what we're looking at here is a summary. This is lung water content is right to left, and these are the different subgroups that we looked at. So on the top, healthy controls, everyone has less than 20% lung water. We defined a cutoff for increased lung water of 20.8%. That's 2 standard deviations above the mean. The patients at risk for heart failure, so these are diabetics, they're obese, hypertensives, that sort of group, around 20 or 25% of them have lung water that's above this threshold for increased lung water. For the heart failure patients, we group them up clinically into NYHA class 1-2, meaning mild, and 3-4, which means like the more severe symptom presentation, and for the HFpEFs and the HFrEFs. And so the mild disease groups are very similar to the at-risk groups, with maybe 20% of the subjects having increased lung water, whereas the more clinically sick patients, NYHA class 3 and 4, about 50% of those patients had increased lung water above our threshold. And we don't expect all of them to be above the threshold because there's different reasons why they're presenting with heart failure. Some of them have increased filling pressures and they can't clear out that water and they're wet. Some of them have signs and symptoms of heart failure for different reasons, which is what we think the added value of this is. So when we break them up into our 2 groups, so this is on the left column here, these are normal lung water content, and on the right column here, this is the wet patients greater than 2 standard deviations above. And what I want to highlight here is BNP is higher, not surprisingly, in this group. There's the clinical signs, crackles in their lungs when they're breathing, and elevated jugular venous pressure in that group. And importantly, outcomes, which is what we're going to talk about next. 30% of those patients who had elevated lung water had an outcome within a year, which was death, cardiovascular hospitalization, or an emergency department visit, whereas only 13% of those with regular lung water had a visit. And if you look at a Kaplan-Meier curve representation of that, you can see that over a year, in the blue curve, if you have normal lung water, you're significantly less likely to have an event, which means death, hospitalization, or emergency department visit, as opposed to those who are wet. And the bottom curve it's the same representation, except it was heart failure specific hospitalization or emergency department visit. We also did univariate and multivariate Cox regression models. And I'm just going to, univariate BMP is always very predictive of outcomes in heart failure. That's not a new thing. But lung water density greater than 20.8% is also significantly predictive of outcomes. And importantly, though, models show that even when you add BMP in the model, increased lung water density is still predictive of outcomes. Almost everything else drops out in terms of being predictive of outcomes when you include BMP because it's so powerful. Our interpretation of this is BMP reflects an increased filling pressure. Not everyone who has an increased pressure gets lung water. Some of them can manage it. Their lymphatic system is okay at draining it away and they're clinically okay. So this is added value. We're saying they have increased filling pressures likely and they can't manage it. And so the nice thing about this test as well is this was very fast and easy to acquire. So it could be added on to any evaluation. You throw anyone in the MRI scanner for characterization of their heart failure etiology, and this can be added very easily to that. So to conclude, lung water quantification by CMR is certainly feasible in patients with heart failure. Increased lung water correlates with filling pressures and is predictive of cardiac events. So it has great prognostic potential in heart failure. Thank you.
Thank you very much, Richard. I think this is a fantastic paper with respect especially to its clinical relevance. It's the first clinical report on measuring lung water. The questions I have is, first of all, the obvious one. If you have New York Heart Association class 4 or 3, people often have difficulties lying flat. Was this an issue in these patients?
So actually, I should have mentioned. So this is a study of chronic heart failure patients.
Mm-hmm.
So they're ambulatory, walking around in the community. Like none of them were actually hospitalized at this point for heart failure. So that was not at all a problem. But in the validation cohort, the 19 patients, they were cathed like within 2 hours of the MR. Some of them could lay flat for 2 or 3 minutes maximum. So we didn't have time to measure a mass or a volume or anything. It's just lie down, free breathing, get the lung water, and come out. But we were successful in everyone in getting the data.
Yeah, no, that's great, because I could imagine, I mean, as a clinician, the chest X-ray may often be confounded by other factors, and then there's always also the notion always that the chest X-ray always lags behind the clinical appearance, and as a clinician, you always wonder, or in many patients, you wonder, is it really the current status? So that in institutions with a rapid access to an MR system, that may actually make a huge difference. So you observed a scatter, and rightfully you said heart failure may or may not be related to lung water. It could also have other reasons. And of course, one obvious one would be cardiac output. And I was just wondering whether you correlated that also with cardiac outputs, or in other words, could it be that those patients with heart failure, yet a normal lung water density, have a low output, and therefore the heart failure in those patients would be explained by the reduced turnover instead of the increased water content in the lungs?
Yeah, we didn't look at that specifically, although in a separate publication, we actually, in 100 patients, we also had VO2 tests in these, and we measured all of the cardiac MR parameters, how they're related to their exercise capacity. And lung water was the only CMR parameter that was measured at rest that was related to exercise capacity. So resting cardiac output or ejection fraction or mass, none of those predicted their reduced, the real primary clinical feature.
Yeah, but it would maybe interesting to look at cardiac output because I could imagine that if you would do cardiac output and lung water, you would cover both typical etiologies for heart failure. And another question was, of course, an obvious one would be to treat patients, for example, with diuretics, and then have an intra-individual comparison before and after. Have you thought of that, or any preliminary results you can share? Or
so actually, can I just, do I have time to show one other slide to address that?
Yeah, we have 1 more minute, but we can extend it by 2.
So this is, we've actually switched the way we acquire the data now. We now have a full 3D approach, a UTE approach, and this data set's acquired in 13 seconds. So you get full 3D lung coverage, and or we have a free breathing version as well. And we actually have funding now to do a prospective acute heart failure study called the MAP heart failure study. So we're going to look at 300 patients, and we're going to image them at admission to the hospital prior to getting diuretics, hopefully, or at least before they take a full effect, and then at discharge to characterize how wet are these people who are hospitalized, how good are we at treating it, and then how predictive are the admission and discharge water contents of them coming back to the hospital, which many of them do, of course.
Wow, that's very impressive. Yeah, as usual, very cool work coming out from Edmund and Richard. So congratulations to both Ian and you for the great work and for sharing that with us today.
Thank you.
So thanks everybody for sharing. So if you could unshare your screen, I just wanted to again thank both Giorgia and Richard for joining us today and presenting their interesting work. And I would just want to point you to the journal club we have in 2 weeks. On December 5, I think it is, on Tuesday, and we'll present 2 papers on automated post-processing evaluation of CMR images, and we'll have Dr. Reising present on fully automated quality controlled cardiac analysis from CMR, and work from Bettina Bessler from Germany, doing an automated texture analysis of myocardial T1 and T2 in acute myocarditis. So with that, I want to thank you for your time. I think at least I enjoyed a lot the last half hour and learned a lot. And again, thanks for the presenters, and wherever you are, I wish you a good day and or a good evening. And until next time, bye-bye.